So let's first recapitulate what we went through in the last two lectures. So basically, what we had was we discussed about the psychoacoustic speech production and perception mechanism. We're starting from your brain, how the speech is produced, what is the chain of events that occurs, how it is then heard by another speaker, how it goes to his ear, and what are the chain of events that happens. Then we most of the lecture was concentrated on articulatory or acoustic phonetics. For classifying different phonemes or sound units. We went through what is voiced and unvoiced speech, and what are their further classifications in terms of the International Phonetic Alphabet, how they are classified based on different physiological parameters, based on how your articulators move, and also how your glottal activity or vocal fold vibration, whether it takes place or not. So that was the basics, the overview of the last class. It was quite heavy, I guess. There were many videos we saw, interesting videos, and so on and so forth. Today is a short lecture, and I would like to keep it not so heavy. It will be light lecture kind of. It will be an easy lecture to follow compared to last class. I hope so, at least. So let's start with let's understand first what's we call speech as a random process. What does that mean? So if you have an event, let's say there is a box and there are balls of different colors, and the event is to pick up a ball of a particular color, something like that. There's a simple some set of colors are there: red, green, blue, yellow, something. So these are a set of, this is your sample space, and picking one of them is an event or a sample in the sample space. So this is a random variable. This is a random variable. A random variable is nothing but a mapping, means giving a number or association with the sample space to a number in the real life. So this is your random variable where x equal to x can be 1, 2, 3, 4 something, where 1 means red, green, blue, or yellow. Or the rolling of a dice, same thing, it's a random variable. So in a random variable, you have a probability associated with an event. If it is a fair dice, simple dice, then there are 6 faces, 6 numbers are there. Probability of x for x equal to 1 or 2 or 3, or it will be 1 by 6 in a random dice. It's a fair dice. If it is unfair dice, one of the sides is heavy or something, then the probability of some of the faces will be higher. In this case also colors, if the number of particular color, there are four colors, if there are more red balls than the others, then the probability of the p x equal to 1 will be higher. So everything has a probability associated with it, every event. This is a random variable. Now what speech is? Speech is a random process. So how does it differ? So a random variable, so is as we saw, it's a mapping. A sample event is there, and we map it to a real line. Whatever sample is there, whatever event occurs, we give it a number associated with a real line. Is 1, 2, 3, 4, and each of them has some probability associated with this. So I am discussing discrete random variable because it's easier to explain. What is speech? Speech is, suppose you have a thought, some thought you want to ask your friend, inquire about the health or how he is. So you have a thought. Now in your mind, so many thoughts can come. We saw yesterday message formulation in your head occurs, then the chain of events occurs. Let's say a thought occurs, and finally what the result is, it's a speech signal. So you asked, the thought occurred, that how are you is finally the result. You wanted to ask about his health and well-being. So you don't have a single number or single point on the real line, but you have an entire signal. In the case of speech is a time signal. In case of other things, other processes, it could be different. It's a independent parameter in case of speech is time. So, but again, if you repeat this event, you want to inquire again. I hope I am audible. Everything is fine. There seems to be a glitch. If you are hearing, please say type Y. Yeah, okay. Sorry, I just heard something. Anyhow, so now again, if you repeat this event, now this will not come exactly. Sorry. Even if you utter the same, how are you, and the same thought comes in your mind, it will not exactly come out to be same. Sometimes you might say it a little bit slower, sometimes a little bit faster. Even the values, it might be similar, but it will never come out to be the same. So each of these signals is a realization of a random process. And obviously, we will only utter once. So there is no way basically how to find probability distribution or probability associated with each and every sample. For different thoughts, you want to ask about your homework or something, your grades, you ask somebody about how is your grade, there is another signal comes completely different. Something, an infinite number of thoughts come in your mind and infinite number of different sentences you utter. At any point of time, if you review your random, what is called probability theory, this is called a random variable. At any point of time, and this from a simple thought that you simple point, or let's map it to our single thought in your brain, whatever signal you get over time, this is called a realization of a random process or a signal. So speech is hence a output of a random process. I hope statistically it is now clear how speech falls into the random process category. A speech signal that you utter is a realization of a random process. It is a time varying signal, one single realization. So why I'm talking all this is last class we had discussed about how to classify speech based on linguistics, basically acoustic phonetics, and that is important because the way of classifying from that perspective, just by listening, it directly corresponds to when we do signal processing to various parameters such as focal tract resonances and performance, and eventually the Fourier transform of the signal. It's different, but on a broad scale, as we said, a speech signal is something always like this. So this is silence. There is something unvoiced sound will come after silence. Then there will be voice sound, and then some unvoiced again, and then again silence. This is what generally happens in any speech signal, continuous speech signal. These are the broad categories. Of course, there will be further demarcation, further differences we can find out. But from a signal processing perspective, these are the voiced, unvoiced, and silence are the three main regions or categories that we have, and their properties uh, are similar, although not the same. This unvoiced region looks like some noise. Silence is very low. Absolutely, it should be zero, but when you record a speech signal, there will always be very, very low some amplitude occurring. So, and voiced is generally periodic and has high energy. You can see compared to unvoiced and silence, if you just take the energy of this part of the signal, it will be high energy. And and then frequency. What is frequency? Is if there is a signal something very zigzag, this will be high frequency. If there is a signal which is like this, it will be low frequency. So you can see that this region, if you separate out, this has low frequency, and this unvoiced and silence, if you zoom in, they will have high frequency. Hmm. This will have high frequency, non-periodic, low energy. So we'll first try to find out. See, we discussed that in any voiced, any voice signal, we saw the glottal, we saw the EGG waveform also when the glottal folds vibrate. So there is a periodic airflow occurring during that time based on the glottal opening instant where the vocal folds open and the vocal folds close, glottal closure instant we say. So because of that phenomena, you have this periodic structure. And this period is called pitch, a uh, very important biometric based on the speech signal. So we will try to find out this pitch or fundamental frequency using autocorrelation, which we'll talk about. I know, I'm sure you know, but what is autocorrelation is, we'll just revisit and we'll apply that to see how it works. Okay. So that is the first thing we will do in this lecture, and then we'll talk about how to segregate from this time domain signal that you have, how to find out the regions which are voiced, which are unvoiced, and which are silenced. How to separate all these three based on this energy and frequency. And this frequency will use something called a zero crossing rate. It's a very simple method, but very efficient method of finding out with good accuracy. It's not the best accuracy, but it's a good accuracy, particularly if the speech is uncorrupted, it's in a clean environment and not noisy environment. You have recorded it. It's a very energy, and zero crossing will give you very decent results, very acceptable results in demarcating which regions of the speech signal are voiced, unvoiced, and silenced. So we'll see those things in this lecture. So first we'll start with autocorrelation. Since we talked about how speech is a random signal already. So this is a standard definition of correlation and covariance. Correlation is this is basically correlation coefficient. So expectation, what is the expectation operator is? It is nothing but the mean. Expectation means finding out the mean. So the covariance is defined as this random variable x is fluctuating. So how is the random variable y fluctuating at the same time? If your random variable x is like this, and your something like this, it is increasing, and your y is also increasing, then you will get a high covariance, and then correlation coefficient is just normalizing that covariance. Normalizing that covariance so that things fall into this 0 to 1 range. So if some signals have some random variables have very high numbers, fluctuating between 1000 and 2000, let's say, other random variables are only fluctuating between 0 and 1, we should have ability to compare such scenarios. So this sigma x, sigma y is the standard deviation. If you divide by them, it comes in the range of 0 and within 0 and 1, and that is correlation coefficient. That is for random variables, and you can extend it to random process. Now, when we don't have now the same thing, let's see for discrete random variables. Here we are mentioning how to calculate it. So expectation of x is mean, expectation y is mean, we all know that. But we don't have this probability of x and y. Generally, in many cases, we don't have. So then we assume that they are all equally probable. If there are n points we are measuring, we just say 1 by n is the probability. And hence this comes up. Otherwise, see, we have to, if that information is available, we'll just use that pi there. So in discrete form, that is what it is. So now we said, see, from a particular thought or a sample point, we have one speech signal. So now what to do? We also here do not have any probability. How do you find out probability of what is this number, or what? The concept of probability becomes difficult here. So in this case, what we do is we think that we assume that the speech signal that we got is a deterministic signal. Just like, for example, you have a mathematical function like a sine wave or this one. We assume that the speech signal is a deterministic signal, and for that you can find autocorrelation. Sorry, I will define autocorrelation before that. See, we saw this. I forgot almost. Sorry. So these are for between two random variables, x and y, what we are discussing, covariance and correlation coefficient. Now if you use the same random variable, then it becomes autocorrelation. Now why do you do so? uh, I think we'll understand if we go to the example of speech, uh, that different parts of the signal, we want to find if there is any similarity or correlation between them. Similarly, if in your random variable some sample points are seem to be having similarity with other sample points, that is what we are trying to find. So I forgot, speech, white sense stationary. I should have talked about this actually. So we talked about speech. So silence, unvoiced, voiced. So based on, we talked about that speech is a linear, we can say it is an LTI system, but only for short intervals of time. Why? Because finally it is produced by the movement of the articulators, the tongue, teeth, all that, lips, everything, and the airflow, the entire vocal tract. Now, there, if you saw your real-time MRIs, they are continuously moving, and that is why we get a continuous speech signal with such varying characteristics. But for short, but they cannot also move at a infinite rate, no. So for short time durations, around 20 to 50 milliseconds, the duration, you can assume that the articulators and the entire voice production system is like frozen. It is a constant, and for that time you can assume that speech is produced by a linear time invariant system, and speech is a stationary signal. So first of all, this 20 to 50 millisecond, it is basically uh, we'll talk about it again later, but it's more accurate to say there are a few pitch periods or fundamental periods, a few periods of vibration of the glottis. For a few cycles of vibration of the glottis, the system seems to be, uh, let's say, stationary, not moving. I can say it is not moving, not changing much. And we consider it to be stationary at that point. So now this stationary term you have heard in probability, white sense stationary and all. That is the correct mathematical, true mathematical way of looking at it. But what does it mean in real time is, the simple definition would be, if you take a Fourier transform, if you analyze the frequency components of the signal, of a stationary signal, they will not change over time. For example, a simple sine wave. If you take a chunk of a sine wave, its Fourier transform will be depending on what is its frequency. If you take this chunk in another time, it will be the same, the Fourier transform. Here, of course, as I said, it is only stationary for a few milliseconds, few tens of milliseconds. If you take a Fourier transform of this region, and if you take a Fourier transform of the next region, of course, it is going to be very different. But within this region, its Fourier transform is, you can safely assume that it is a stationary signal, and its Fourier transform is valid, and it is not changing, or it is a true Fourier transform. So we'll discuss later in the next class about this why do you need time frequency analysis and short time Fourier transform? There you will get more clarity regarding what I mean by stationary. But just for now, just consider that because the glottal in the voice production system is more or less constant for certain short durations. In those times, we have a stationary signal, a signal which characteristics are not changing for the short duration, not changing, and hence we can use it using Fourier transform and analyze it, or some uh, we can consider it as a stationary White-Sand stationary process, or even a strictly stationary process for that matter. So now why I'm where I was, yes. So if you recall your probability lectures, that autocorrelation function, whatever we had, instead of x and y, we'll have the random variable at time t and random variable at time t plus tau, where tau is a lag, that is defined as the autocorrelation function. The expectation of this parameter at time t and time t plus tau or t minus tau, however you put it. So that is the autocorrelation function of a stationary process. It is a function of the lag. So it does not matter if you put t at some 5 seconds and 10 seconds you measured, or you measured at 7 and 12. This autocorrelation function will remain the same. It only depends on the lag, the difference, the time difference between the time intervals. So there is a property of stationary random process. Now for a signal, as I said, we have to consider the speech waveform as a signal, because we cannot simply utter multiple times the same sentence. It does not happen. So we think that it is a deterministic signal. We take it as a deterministic signal, and for a deterministic signal, the autocorrelation will simply come out this f dash is a conjugate if it is a complex function, but in our case it will be all real. So it's simply this whatever is your signal, yn, it is represented here. We have been using Sn or Xn. So simply the lag, a time shifted signal, and the signal itself is the inner product basically of one signal. If you have a signal like this, and if you have the same signal you shifted by certain units or certain duration, and you multiply and find what is the similarity. So this is the autocorrelation signal, autocorrelation or autocorrelation function. Sometimes it is also called autocorrelation of a discrete time signal, of a deterministic signal. So how is this useful in calculating our period? That is our next thing. So let's imagine a sine wave. Now, if I keep shifting my sine wave, it is a complete, is a what is called infinite sine wave. If I keep shifting my sine wave and then multiplying, okay, I shifted by this amount. Now if I did shift by a complete uh, Hey, a complete cycle. Okay, this is a complete cycle. If I did shift by a complete cycle, this will be this one. If I did shift by a complete cycle, what will happen? It will again align itself with the it will again align itself with the same signal. If I shift by a complete cycle, so 2 pi, if I shift by 2 pi, it will again align itself. So if you plot the autocorrelation function as a lag, so wherever there will be 2 pi lag, wherever there will be 4 pi lag. So first, when there is no lag, the signal multiplied by itself, it is nothing but the energy square of the function, and then you integrate or sum it up. Then again, you'll find at 2 pi, it will have high values, and at 4 pi, it will have high values, and so on and so forth. So basically, if you take the peaks, the distance between the peaks of the autocorrelation function, it will give you your period. So this is the motivation behind using the autocorrelation function for speech signal. So what we do is our speech signal in voice regions, it has a sort of periodic structure. So we determine the autocorrelation function for it. Zero lag, it gives energy. Then if this is your period, let's say T naught, your fundamental frequency or pitch will be 1 by T naught. Okay, so or if you want to determine in terms of n naught because it's a discrete time signal, that's also okay, and then you can convert it into frequency in analog form. That's fine. So, but just let's talk about in this analog terms. It becomes easier to visualize in our mind. So we have an autocorrelation function. If you keep going, somewhere you should expect wherever there is T naught, 2 T naught, then it will have a peak. Now it could have in between also certain fluctuations. That is because it is not a pure deterministic signal. It is not like a sinusoid. But if you have something like this, then what you can do, you can you can track the envelope. You can track the envelope of this autocorrelation function, and then you will find that in the envelope, if you track the envelope, I will draw again because this is a little messy. So there are multiple peaks unlike in a sinusoid, but if you track the envelope will be something like that. You can fit a polynomial function or something based on this so many peaks you have. So you can then get the largest peaks, and you will find that that distance that you get should correspond to your pitch period, or conversely, if you take the inverse, you can determine the pitch frequency. So this is the concept that is utilized for finding out the pitch period of the signal. So what is done is, we have our voice signal, speech signal, where silence is done, voiced, unvoiced, and this one. First, you have to determine what are the voice regions. Okay, what are the voice regions? You have to determine. How we will determine by some algorithm somehow. Or let's forget about determining. Let's simply, you have the speech signal. We'll break it up into frames, small frames, because we said no, because speech is stationary, and you can see from the waveform that it has what is called similar characteristics only for short durations of time, stationary characteristics. Its characteristics do not vary, only for short durations. So let's say 20 millisecond frames you broke it up. Then for every 20 millisecond frames, you apply the autocorrelation function. And you determine the pitch from that. So you will find wherever there is unvoiced signals are like zigzag, like noise. So you will not find those pitch period characteristics, that periodic characteristics in the autocorrelation function. Those peaks you will not find, prominent peaks, and your estimate of your pitch will become some very high, something pitch frequency will become very high. Oh. But for voiced, wherever there is voiced, you will find some reasonable estimates of your pitch frequency. The pitch frequency in adult humans generally lies from around 50 is generally for children. For male, it's around 100 hertz. For females, around 200 hertz. But it varies between somewhere around 50 to 400 extreme cases. Some adults also have very high pitch. Oh, sorry. I think children are having high pitch, so 400 should be for children. Some males which are very, very deep voice or something, they have very low frequency. But this is the range around, very extreme range. Generally around 100 hertz male, adult male, 200 hertz adult female. That is the pitch frequency. So you will find this all over the place, and then the voice frames, a few voice frames, you'll find that they have a cluster of values in the pitch frequency range, and that's how you can determine in a very simplistic manner what the pitch frequency is from the autocorrelation function. So mathematically, let's see what that means, how we implement it. So we have a signal xn, but we'll represent it as okay, let's put it xm because it's mentioned like xm. So we have m in your signal. Now at a particular point n, n sample, we'll put a window of unit height, but this may not be of unit height. We'll discuss again. Sorry, this may not be a rectangular window. It could be other windows also. We'll discuss about this in the coming lectures. But let's assume it's a window of certain length. So multiply with this window, so rest becomes all zero. Only this portion of the speech signal remains. Now this signal, so this xm, it will become w n minus m. Okay, this signal will be xm w n minus m. So this, now you take the autocorrelation function. Okay, so from this signal we can call this as x of n, the nth point, the center point is n, but your index or time axis is denoted as m. With this signal, you take the autocorrelation function. So basically, you will take x of nm, x of n. You write m plus l, m minus l, whatever, what, rx of, or you can say r of n at the point n. You are taking l. Now then, you can move this. You can move this by a single sample and calculate the autocorrelation function for each and every, by a shifting window that is shifting by each and every sample. Or you can choose not to do that. Maybe some overlapping frames you can do. Your frame length is, let's say, of 20 millisecond. You can choose to do 10 millisecond shift, so that's 50%. You can do like that, or you can do by each and every sample. Those are things that are in your control. You can choose to do that. The common thing is, a common way of doing this is, whatever is your frame size, this is called frame size, your window size. The frame shift is 50% of that. So the other window will start from half the midpoint of the so if your window midpoint is this, next frame will start like this. If your, this was your some frame I, the frame I plus 1 will be this one. So I hope you got what I'm trying to say. So by doing this process, for each and every frame, you calculate the autocorrelation function as a, where you will get your lag, and these are your values. For voiced signals, what you'll do is just trace the envelope. You'll track the envelope of the signal. This is called the envelope. Okay, you'll fit a polynomial. Basically, easy way to say is to fit a polynomial to the peaks of the function. Okay, the peaks of the autocorrelation function, and then from that, if you find a distance between the different peaks, the average distance should give you the time period or pitch period. So I hope what I said in this lecture, I hope you were able to grasp. There is no time left. We'll discuss short-term Fourier transform, periodogram, and energy and zero crossing rate. These are all short time. These are all called short time analysis of speech. These are all called short time analysis of speech. Short time analysis of speech. We'll discuss about these things in the coming lectures. So that's it for today.